Okay, let's get started. As I mentioned before, a lot of these pages are from previous years. Nice pictures, stuff like that that I just throw in because I think they help make the point. We were working on fasteners. We were working on Was ist los mit dir? I don't know. Don't do that again. We were working on the fact that sometimes when you bolt something like an angle, the load had to come down out of the top leg and go down in the bottom leg, and you lost a part of the angle, thereby making it less efficient. This is for staggered fasteners and how you handle the loads in a plate or an angle in under those conditions. We mentioned that the length of the line, should the tear line decide it is too hard to fail it across here, it's just easier to go ahead and skip over to the next hole, even though it's longer. We mentioned that there were tensile stresses and shearing stresses. You would normally think, let's just take this total length across here, then find this squared plus that squared, take a square root, find that length. How much ever longer the hypotenuse is other than the leg, you just add that amount, you'd be okay. Physically, that's true. Structurally, it's not true. What we've really found is if you go from this hole, don't go straight across, but move over to this hole, the previous length of this line is increased by s squared over 4g. This was our spacing. And this was our gauge, like the gauge of a railroad that runs down the tracks in the direction of the load. So this original length leg of the triangle is not that much longer, but it's that much longer, and that works out really close for the structural strength. And it includes the fact that it is longer, but also that different kinds of stresses are acting on the plane, other than just nice old tensile stresses. There's several reasons why you would do staggered fasteners. Number one, if you put them side by side, you do destroy 2 holes worth of strength, and you don't pick up any extra length, so you may want a little extra strength. Sometimes the member itself is slanted with respect to what you're connecting it to, so when the load comes down, it sees no holes, 1 hole, maybe 1 hole in that hole, and so on. There's your S, there's your G. Old notes, gross area for a plate, just the 2 dimensions of the plate. Net, 2 dimensions minus the number of holes that you cross as you go through a tear line, times the diameter of the hole, which is the diameter of the bolt, plus a 16th plus a 16th, times the thickness of the plate. Sometimes that's not the whole story. For plates, this is good, but for angles that are bolted only on one leg and have an outstanding unconnected element, you will have to reduce it by a reduction factor. Those are listed for different cases. Diameter of the hole, diameter of the bolt plus a 16th for fit, damage, effective area. In this region right here, you do get a stress. Down in here, load over area gross. Down in this region, you get load over area net. And it's increased by U, or the load is decreased by U. Take your choice which way you work it. There's your net area. Now, how bolts really work. Here's a plate. Put 200 kips on the plate. I'll tell you now that I tested these bolts. Around 80 kips, they get a little deformed. but they'll go on up into the yield range and keep picking up load. At 100 kips, they're just pretty much trash. So out of 200 kips, the first load hits the first two bolts and 80 kips on each bolt drops out. Then that leaves, 80, 80 is 160, that leaves 40 kips in this region right here. And you say, well, why aren't they all 80s? Because until these bolts fail a little bit, allowing this plate to stretch, see if this bolt doesn't do a little bit of this, then the plate behind it hasn't moved. So until it has a little bend in it, no load gets on through because the plate isn't allowed to move, and so you don't get any load. But at 80 kips, they're deformed pretty enough that the plate right here can stretch, and then about 20 kips comes out these bolts, and then you get no bolts, no plate, no force. Increase it to about 400 kips, the 80 runs on up to about 90 each, about 70 each comes out here, about 30 makes it down into this pair of bolts, and about 10 make it down into that pair of bolts, and these bolts here say, huh? Nothing down there. Nothing made it because the plate hasn't stretched down in that region enough for those bolts to pick up some load. Here's 580 kips, 100. Now you see these bolts have gone plastic. They have deformed like that. You know, they had 100 in them when they only deformed maybe this much. And then they held 100 when they deformed that much. And they held 100 when they deformed that much. So they got 100 and 100, 60, 20, 10. Here's 760 kips applied, 100, 100, 100. These have all failed fully plastically, but they're still holding the load. 50 got down to here, 30 got down to here, and finally, which is where we design it, all the bolts are equally loaded. Now you can take that to extremes. If you took this down here for 40 feet, I don't think there's any way it would really work, because these bolts would hold 80 till they went up into the ultimate range, and then they'd break before this bolt down here even knew what was going on. So you'll find in the specifications you will pay a penalty if your bolted connection is too long, and they're taking that into account. Here's a plate. It's got 900 kips on it. At ultimate load, there will be 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, gee, that's convenient. 9 bolts, and therefore 100 kips will fall off of each bolt. It's just like water running down a trough. This hole is big enough to let 100 gallons a minute out. You're putting 900 gallons a minute into the trough. When I ask you what is the flow right here, you would say 900 gallons a minute. If I ask you for the flow of water at this point in the trough, you'd say, well, that trough has a hole in it, and it let out 100 gallons a minute. So how much gallons a minute is left? 800 gallons a minute, and that's how much load is left. So there's 800 kips going to flow across this pair of bolts. Take out 200 from 900, it's going to leave you 600 kips of load at this row of bolts, and on the last row of bolts you'll have 300 kips trying to break across that line. Now, if you study a break line that goes across here, you'll have to reduce the load trying to break across those two bolts by whatever's been removed before it. If you try and find out, might this break across here, well, then you'll find the full 900 kips of load is in there, and the 900 will try and break across here, across here, across here, and back, across 3 holes. But, of course, you do pick up some extra s squared over 4g 2 times because you have 2 slant lines. This is your gauge running down the axis. This is your spacing. So there's an equation for it, but I don't think you need it. Load is equal to the number of bolts remaining on that line and further to the right, divided by the total number of bolts times how much you put on there. I think it makes a lot more sense just to look at it and see. Yes, sir.
When you have a bolt,
Yeah.
and you have
Yeah.
the bolt,
If you make it out of glass, yes. But we don't do that very often. You could try it. Because steel is so ductile, the bolt can withstand, I'll show you some pictures later on, massive amounts of deformation, where it looks like the thing should have broken long ago. And the truth of the matter is, it's just right about here and has not let go of its load, didn't break. They look like this all the time once you take them out of there. And they're not broken. You say they sure scared the dickens out of everybody. Life is tough. Don't go in our buildings if you don't want that to maybe happen, but you won't die. Here's some more of the same. Has some reasons for you. The load is coming in, can't get in this little piece, it's lost to you. You will be a measure of X bar divided by L. 1 minus X bar over L. Here you had welded on the sides. You have the same problem. Even though the welds can get in there, you're losing this piece. If the welds are long enough, we can live with it. Here's where you welded on the two sides of the plate. You didn't think you were going to lose anything. You don't have any outstanding elements unconnected. Well, you really do. This little piece of the plate itself, the stresses had to go around to get into the weld. If you put a weld across the end, 100% efficiency. Everybody's got a path to transfer the load from the top plate to the bottom plate. If you weld just across the end of an angle, that's really tough. And they just say, look, suck it up, where you don't even get an angle. You just get the plate that's down there on the bottom. So the cross-sectional area of that would be reduced down to the thickness of the angle times the leg length that's welded to the plate. Here's a nice long weld, plenty of time for the loads to get out. U is a 1. Here it's worse, therefore U is less than 1. Here it's horrible. Look at these poor people trying to get out this little bitty exit. U is 0. Now, the CVE and a lot of people like to, when they work these problems, they like to come up to the hole, and if they see a slanted line coming up, they say, well, what I'll do is I'll subtract the S squared over 4G from the hole dimension when I put it in the equation. And I'll just go ahead and use the distance across here, but I just won't take off as much hole. So in other words, basically, I'll still have this dimension minus 1 hole, and because of the slanted line coming up, I'll make this hole a little smaller. That drives me crazy. I can't remember all that nonsense. But some of the calculations of the book are done that way. You'll see the calculations are the same. I highly recommend you just find the gross area of whatever you're talking about. Take off every hole along the tear line, 100%. And if any of the tear lines are slanted, then add to the strength, the cross-sectional area, an S squared over 4G to take care of the fact that this is longer than this. You've already taken into account this by using the gross area. You turn the gross area into a net area by taking off 2 holes, and then you add the added strength due to the slanted line, S squared over 4G. Now that's not an area, that's a length. That, of course, then has to be multiplied by how thick the plate is. Your choice, but I just can't keep that other thing straight. Because I come up, I see 2 holes, and so do I do that twice? Which hole do I do it for? Either hole? I don't know. We want you to compute the smallest net area for a plate shown in figure 315 on the next page. And I put a load on there. I just like loads on things. So I put 1100 kip. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I wonder why. He says the effective hole diameter is 1 inch bolt plus a 16th plus a 16th. Then the calculations for line A, B, D, E. Here are your failures. A, B, D, E is possible. A, B, reach out and touch someone. C, D, E is possible. Something unnumbered, C, something, and G is possible. It's getting less and less likely because the load's being reduced as we go down the plate. Here's a possibility from there to there to there, way over to there. And I'm not doing that. There's no way that's going to fail like that. It's either going to fail straight across here, if this is pretty far back, or it's going to fail right across here if this is an extra hole but you get some added strength. Or, you know, it can't fail across here. That's only one hole. It'd rather fail across 2 holes. So there's not too many things you have to check. First, you're going to check Alpha Baker Dog Edward. Alpha Baker Dog Edward, straight across. It's 16 inches across, 5, 10, 11, 12, 13. It is 16 inches across. He'll subtract out 2 holes of 1 1/4 inch width. Notice we're only talking about the length of a line here. That's 13.75 inches across the plate. Therefore, the net area is 13.75. The plate is 3/4 of an inch thick. Gives you 10.31 square inches of steel if it fails across A, B, D, E. If, on the other hand, it fails across A, B, C, D, E, A, B, C, D, E, then we have a length of 16 across. We'll subtract out 3 1.125 inch holes, and we will add 2 slanted lines, each line having an S squared over 4G. There's your 2 slant lines. There's your spacing along the railroad tracks. Divided by 4, here is your gauge parallel to across and parallel to the railroad tracks. How far it is between the wheels. So it's 10.1. And you will be picking the lower of the 2. In other words, that's less net area. And then that's going to be, this is just the length. You can check that's just the length. That's 16 inches. This is just the length. 2 times spacing squared, that's inches squared, divided by 4 times the gauge, that's inches. Inches squared divided by inches is inches. This is just the width. Somebody's going to have to multiply that times T before we're going to be finished, or we're not going to have an area. So what he found on the previous page was it was 13.75 inches across the plate. There he multiplied it times the thickness of the plate. There's his 10.31 square inches of steel. For the second line, he has its 13.52 across the plate. That's smaller than he had on the previous page. That's why he didn't actually do this calculation. He says, let me just see how far it is across the plate, 13.75. Let me see how far it is across the plate, 13.52. He says that's the shorter distance across the plate. Then he multiplies that times the thickness to get the area. That is his net area. How's he going to turn that into an effective area? How? They're going to multiply it by U. What is U for a bolted plate? It is 1. That's correct. And so he doesn't have U's written down here. But that's a thought. You know, every net area is going to have to be multiplied times U, even if it's a 1, before you're finished. Now, this is pretty much what we said about each fastener resists an equal share of the load. In this case right here, if you had 1,100 kips, then at this level right here, you'd have 1,100 kips. Right at this level, you'd have 1,100 kips. Right at this level, you'd have 1,100 kips. Because as of yet, all the steel to the right of the lines that are shown, they're still subjected to the 1,100 kip load. Nobody has yet pulled some loads out. The minute you get to this point, on the other hand, you can't fail across here or anybody downstream without 3 bolts having pulled out their full share of the load. 3 out of 11. That's 100 kips each. So the load along this line and anywhere back here till you hit some more holes is going to be 800 kips. Now, if you're talking about an angle, then what you can do is just go ahead and flatten it out into the plate from which the angle was made to get your gauges and your spacings. It's a lot easier to see. The truth of the matter is, in an angle, here's one drawn in 3 dimensions. The tear line comes down and across, or the tear line may come down and across. Here's your spacing. Here's probably, as I say, is another hole up in here. Finding if that hole is in that line, then there's your gauge right there. The distance from here on down to here. You say that's kind of hard to see. We'll flatten it out. It makes it a lot easier. Here is an angle that has been flattened out. It is a 5 by 5 by ½ inch angle. If you look on page 1-48, it's on page 60B in my notes, so it's coming up, you will find a list of numbers that says when you have 5-inch legs and you want only one hole, put it at 3. That's the common thing to do. If you want 2 holes, look at all these people pulling out their books. And, you think I'm lying? I wouldn't lie to you. Golly. He says, no, you're not lying. You're just wrong so much of the time. I'm just checking. Okay. If you want 2 holes on a 5-inch leg, then you'll go at 2 inches and 1 3/4 of an inch. Now, that's there just because they fit. The guy can get a wrench on it, or the lady can get a wrench on it. But it doesn't have to be. It's not required. It's just good practice. Unfortunately, when the load comes down and has a tendency to break from this bolt to that bolt, maybe back to here, the full load, then I need to know how to add the S²/4G for this line, which is around the corner. What you can do is basically the gauge length from this bolt here to this bolt here is just 3, no, you went too far, sorry, minus a half of the leg thickness, plus here, no, you went too far, please back up, half of the thickness. So the gauge length is 3 plus 2 minus 2 halves minus the thickness. Just that easy to get the gauge on an angle. Then the spacing, of course, is right here, whatever that spacing is. He hadn't shown us, so we'll have to find one where he shows us what that spacing is. If the plate itself, if you're looking at the gross area back in here, you'll find that that is a 7.5 inch plate, because it goes from here to here, which is 5, and then it goes from here to here, which is 5. That's interesting. Oh, that's a different angle. I wanted a different one. The area across here, or the length across here, is 5 inches. You went a little too far. Plus 3 inches. You went a little too far. 5 plus 3 minus a half, 7.5 inches across there. Here's his problem. He has a 8 by 6 by ½ inch angle. If you want to know which is the 8 and which is the 6, you could go look up why he picked these numbers. That's in the 6 inch leg. And why he picked these numbers, those are in the 8 inch leg. It says got staggered fasteners. They're for 7/8 inch diameter bolts, so the hole size is 1 inch. From the dimension tables, he says you can get the gross area. You'll find that on page 1-42, 6.8 square inches. If you drill holes in it, that's your problem. I gave you 6.8 square inches when I delivered it to you. The net area on line ABDF. All right, here's the end view. Here's the top view. Here the thing is flattened out. He says the gauge length on this one is 4 1/4. Let's see if I like that. 2 1/4 plus 3. That's 5 1/4 inches. 3, 4, 5. Minus, it's a half. That's right, 4 3/4 inches. So we'll check out line ABDF. ABDF goes straight across. You'll take the gross area, you'll subtract 2 holes. No slants for you. You'll take the gross area. Each hole has got a 1 inch loss of steel across the plate, and it's a ½ inch thick. Be nice if you put units on these so you really see this is square inches. This is a ½ inch thick angle. This is a 1 inch diameter hole. It was, yes, sir. There it is. That's why it's a 1. It's correct. And then there are 2 of them as you go across the angle. 5.8 square inches. If you get a net area someplace smaller, someplace else, then we will not even need this calculation. A, B, C, E, J. A, B, C, E, J. Well, he's skipping one. He probably ought to be checking A, B, C, D, E, but I can live with it. He says, look, I can't check them all. I show them how to check a couple. They ought to be able to figure that one out on their own. I say, okay, how many slant lines would you have if you went A, B, C, D, E? Well, you'd have 2 slants, an S squared over 4G for that one, and an S squared over 4G for that one. But doing the one he wants to do, I'm going to give you the gross area straight across. I am going to subtract 1, 2, 3 holes. Let's count them up. There's 1 of them. There's 2 of them. He subtracted 3 holes. Then I get to add an S squared over 4G term where the spacing is 1 1/2 and the gauge is 2 1/2. There's your 1 1/2. There's your 2 1/2. There's your S squared. There's your 4G. Whoa, what is this, man? He's doing it the wrong way. Oh, he's doing it that funky way. See the plus? plus S squared over 4G for that slant line right there. And since he's calculating straight across, he only gets one. You and I were talking about getting two, but you know, he's not checking that line. He's checking A, B, C, E, G. There's his plus S squared over 4G. Question. I see it in your face. Something doesn't make sense. Maybe not. Maybe you just had a little heartburn there. Questions? You say it's pretty obvious, pretty simple, pretty straightforward. It is, but until you kind of digest it, yes, sir. Okay, see, you see this number right here? It's a distance across the plate. To turn that into an area, he has to multiply it times the thickness. Everybody has to have a thickness on it. That's correct. See, because this is the length across a hole, and this is an added slant line, distance. Both of those are at some time or another got to be multiplied times a thickness to turn the length into an area. And that'll be a very common thing you forget to do on a quiz. You're so happy you got the S squared over 4G, you forget to put a T on it. Yes, sir. Then he's right and you're wrong. The question was, what if you check a line and you don't get the same answer the book gets? Then you're wrong. And the reason you're wrong is because there was a worse line somewhere else that he checked. The reason was he probably forgot it in class a couple of times, and then some student says, looks like that other line would be worse. And he did it, and uh-oh. And so in his book he wrote just that line. Because I don't know. I really don't know if it's better to go across here or better to go across here. Generally speaking, much further back is not going to be worse. Although that is picking up an extra hole going like this, I'd have to check them all. Now on an exam, you know, you're not going to have to check them all. I want to know, can you check any of them? And if you can check any of them, you know, I would say, what is the strength across line A, B, X, M, P? You say, nonsense. It couldn't possibly happen. Well, that's not the question. The question is, can you do it? Okay? Now, these are the same thing laid out flat with the gauge numbers written a little bigger and more clearly. Here's line A, B, C, E, G, and all the calculations in the S squared over 4G's multiplied by T. So take a look at any of these pages that are, you know, just complementary to the previous stuff. Here's the page I told you that the angles would give you the place to put the holes. Once you get down to a 4-inch leg, you can't put two holes in it, so there's only a G1. In a 6-inch leg, you have the choice of one hole or two holes. Now, is this an extension of the previous problem? Page 60, page 61. All right. Now, oh, that's right. Sorry, I entirely forgot about that. Since he's checking this failure line right here, he no longer has 100 kips of load on there. He no longer has the load P. Since he's studying behind that bolt, when that bolt fully took out some load, that load removed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 out of 10 bolts. It removed 10% of the load. Now, generally speaking, I really don't want to go do all this calculation for that line and this line and that line and this line and that line. It would be nicer if I could just get the net area and write it down. And I was getting ready to write, in fact, I think we did write down this net area. But if you want to be able to compare it with a previous net area that you calculated, somehow you're going to have to admit to me that the load that gets to that line is not full load. It's only 9/10 of the load because you passed up 1/10 of the bolts. They already took that load out. And so what everybody does is, rather than doing all the calculations with this net area and doing all the calculations with that net area, they just say, look, you know what this net area here is? I say, yeah, I just wrote it down. He says, you're wrong. It's 10/9 bigger than you have written down. What? How can that be? Let me check my calculations. He waits and grins and lets me recap. I said, no, you're wrong. I said, the net area across that thing right there really is 5.413 square inches. He says, it's not effectively that much. He says, because it's only hit by 9/10 as much load, you need to take that area and multiply it times 10/9 before you can compare it with this area on this line. Now that may have your head reeling. You may say, got a brain, I don't know where you are at this yet, but it makes sense. In other words, the area here calculated as net was impacted by the full load. The area down in here was a net area, but it only got hit by 9/10 as much load, so I'm going to multiply that area times 10/9 so I can compare it to see if this guy wins or this lady wins. And that's what's going on this page here. So this thing should be multiplied by 10/9 to obtain a net area that can be compared with other lines that are having to resist the full load. Therefore, this is how much net area it has. Then he says A, B, C, D, E, G. Good heavens, where is that? A, B, C. Oh, that's the one I thought might be interesting. A, B, C, D, E, G. You're going to have 1, 2, 3 slant lines. So you're going to take the gross area. You're going to subtract 1, 2, 3, 4 hole widths times T. You're going to add a S squared over 4G for this one times T. You're going to add S squared over 4G for that one. You're going to add an S squared over 4G for that one times T. And then that'll tell you the net area. Incidentally, the net area well, anyway, let me see. So where have we got that? We ought to have gross area. Here's 1 bolt, here's 2 bolts, here's 3 bolts, here's 4 bolts, and there ought to be a thickness times plus S squared over 4G for 1 of the slants, 2 of the slants, 3 of the slants. Now those are the net area. Where's the effective area? Is this an angle? The effective area. Where's my U? Where's the effective area? Where's my U is equal to 1 minus X bar over L? All of the outstanding elements are connected. There are no outstanding unconnected elements. Connected, connected. U is equal to 1. Good. So then we can go ahead and find out how strong the thing is. Oh, there it says right there, both legs are connected. U is equal to 1. The effective area is the lower of the two. We have 2 strengths. One will be based on fracture, and one will be based on yielding. Based on fracture, we have the effective area times ultimate, 293. Based on gross section yield out in the middle of the member, we use only 36. The yield times the full gross area, 244. We still don't know who's a winner because one of these guys is really dangerous, going to have to knock down to 0.75 of its value. The other gets a 0.9. Based on fracture, 293 times 0.75, 220. Based on yield, 244 times 0.9. Give me a break. Pure chance. Well, it wouldn't happen in another 100 years. They're both the same. You would take the lower of the two. Another example, 5 by 3 by half, finding the gauge length is 3 inches plus 1 3/4 minus the thickness of the angle, 4.25 inches. That's if you have a 5 by 3 by ½ inch angle and put one hole in the long leg. If you put two holes in the long leg, this is where they go. G is 2 plus 1.75 minus the thickness of the angle. That's the gauge. Quick and easy to calculate. Wow, man, what a weenie pop quiz that year. Here are the tables where all this stuff is coming from. Remember we used F sub U and F sub Y? There they are. Page 2-48. Another example. Determine the smallest area for a channel. Works just like everything else. Smallest area for the channel will be the gross area. Then you will take off one hole and have no slant lines. Then you will check going across two holes and then get a slant line. Here's your area. Here's one hole with no slant lines. Here's your area. Here's your hole. Remember now, the thickness of a channel is a weird number. That comes out of the channel tables. Thickness of the web. There's a hole. Here's a hole circled. Here is a minus times a minus, one slant line. 2 squared and 3. 2 is the spacing. There's the spacing. Here's the gauge, 3 inches. Now he doesn't carry that on out because now then area net's not area effective. So I went ahead and did that. He didn't ask for it. You shouldn't do it if it's not asked on a quiz. U is equal to 1 minus x bar over L. This number right here is listed in the channel tables. See this on page 62A and B. What we got in 62A? Here's our channel. It is a C 6 by 13. There's the web thickness, 0.437 inches. Next page probably gives you the X bar. Here is, that means wrong. Don't do that one. That's X plastic. This is the one you want, X bar, for a 13.514 inches. That's where the centroid is. That's from there to there. So 1 minus, there's your 0.514 inches. Where did that come from? There, huh? Right up here, you have the spacing length is from bolt to outer bolt. 4 twos, 1, 2, 3, 4 twos, 8 inches. That's the length of the connection. You must reduce the strength of your calculations by multiplying them times 0.936 to take care of the fact that around the ends of the channel, the loads can't get up into the flanges. They have a hard time doing it. And so area effective is area net times U. You got 3.31 times 0.936. This is the area that you will use for area effective. We're going to use that in our gross section yield or our net section fracture calculations. I don't remember. Both? Well, that's a safe way of doing things. Fracture only, right. In other words, you can wear a belt and suspenders, but it's probably overkill. So this is an effective area for use in rupture calculations around the bolts. In the gross section yield end of things, you're going to be using the gross area and the yield stress. Then we have staggered bolts, just weird situations. We don't do them. I think many times a text will include those things in case the prof thinks it's important and doesn't use his book because he didn't have it. That's for bolts in the web and in the flanges of S shapes. And it's just very seldom done. Here's where I'm getting all this stuff from. Chapter D, Design of Members for Tension, 16.1-26. You'll see immediately why I brought it out. Tensile yielding in the gross section. There's the equation Segui gave us. That's where he got it from. What does he multiply it by? 0.9. What is that name? What is that thing called? It's a strength reduction factor. There's many of those, but this one in particular is on which side? The load side or the resistance? Oh, I think I just gave it away. Yeah, it's a resistance factor. That's right. It's applied to the resistance. You already have factors to go with the loads. 1.4 dead, 1.2 dead, those kind of things. Here's your tension rupture. F ultimate, area effective. Someplace else, he's going to have to tell you how to get area effective from area net. He will. Here's your reduction, your phi for fracture. There you go, effective net area. How do you do it? Well, you multiply it times U. Well, now you got to tell me how to do U. He says, well, it's in table D31. Where the devil is that? I don't. There it is right there. All of these things, they refer like spider webs to different things, you know, and you got to be able to go dig them out because that's all you bring with you to an exam. Sometimes for bolted splice plates, this doesn't work as well as we wish it did, and therefore, let's say if you're doing a splice plate, the area effective can equal to the area net. That's bolted plate to bolted plate. However, no greater than 0.85 area gross. Why is that? He said, because something fell down one day. And since we don't want it to happen again, as soon as we find out, we'll let you know, but no bigger than that for a splice, bolted splice plate. There are your U factors. Here is is this Segui or specs? How do you know it's specs? Looks just like Segui. Why? They've got a section number up here. 16.1-18, that's the page number. Came out of section B4. Gross area, how to calculate it. Net area, how to calculate it. Time is it? I'm having fun. Yeah, I still got time. There's that one I was telling you. I told you, well, it is. There's some for S shapes and there's some for channels bolted into the flange and the web. Just, I don't think I've ever seen such a thing. He's got an example. Forget it. Block shear. What is block shear? Well, it used to be we'd bolt an angle to something. We didn't have any problem with this. But then they started making this nifty steel. The old steel was like A7. I don't know, had a yield stress of 20 or 22. But as the steels got stronger and stronger, we started using thinner and thinner shapes. As we used thinner and thinner shapes, all of a sudden we had these little corners tear out. Didn't break across the holes, didn't come out, break out in here, little corner broke off. So we said, all right, we're going to have to do something about that. If you'll notice that when this thing pulls, you have a shearing stress on this surface, and you have a tensile stress on this surface. So now that's going to be a kind of a combined item because the shear permitted stress is going to be smaller than the tension permitted or limiting stress. As a matter of fact, it's 6/10. In fact, it is so much 6/10, we don't even have a name like that. We don't have a F yield and shear because it's 6/10 of F yield and tension. And you don't even have a F yield and tension symbol in your book. All you got is F sub Y because that's all we have is tension. You say, what happens when we have shear? It's 0.6 of F sub Y. How about ultimate? Same way. It's 6/10 of F sub U, which is more properly said F sub U in tension. And 6/10 of that is the F sub U in shear. See you next time. Thank you, sir. Yes, sir.
Friday is the time I came and talked to you about. I'm going to be gone for a week.
Okay.
And then I'll have all those assignments to you the Monday I get back.
That'll
By
be
your
fine.
office.
That'll be fine.
Thank you.
And don't come by my office, just put them in here.
Put them in here.
Yeah.
Do I need to come up here to get you to initial them or anything like that?
No, just say Lowry. I went on a trip. Lowry has excused his absence. They'll know. You wouldn't dare write that down if it wasn't true.
I had a question over the 9/10, 10/9 thing on staggered bolts.
I don't blame you. Let's just say that I found the effective area right here.
Right.
It gets hit by the full load, doesn't it?
Right. Yeah. I
Now then,
understand.
you probably wouldn't check this because the effective area would be the same.
Right.
But if I wanted to compare how strong this section was with respect to that one,
Right.
do you see how I would first say, the 600 kips applied here never made it to this section.
Right.
And therefore, what I really, if I want to compare this section's area with that section's area to see who's worse,
Right.
I really ought to take off 2/6 of the load
Right.
because only 4/6 gets here.
Yeah. Okay.
What I can do to account for that is multiply this area times 6/4
Yeah.
to compare it with this area.
Okay. So if you take from this bolt to this bolt, would that be 5/6 of the load?
That's exactly right.
Okay.
See, because it's like holes in a trough.
Yeah.
The water hadn't made it out of those two yet. If it's going to fail across here, you only had one hole sucking water out of the trough.
Right.
So now then, across this plane here, you have 5/6 as much load.
Right.
So when you calculate the true net area or effective area, please, if you would, multiply it times 6/5 so I can quickly compare it with this area.
Right. Okay. That makes sense.
Okay.
Thank you.
Clarified some stuff for these guys. I have another question. On the homework? That's a question about the A24-2.
A242, all right? That's a good steel. I love that steel.
And it was for a plate. So I went over to this table here for plates,
Yeah,
and I noticed that there was 3 different strengths for that plate
okay.
with no little symbols there. So I was wondering,
All right,
which
let's
one to
see.
use.
Let's see what you're talking about. So these are shapes. These are plates. A242. Well, these are designated. By that I mean I'll tell you what the plate is. A242 grade. They have grades on them.
It had it on this one. Do we
Yeah.
assume the same ones for that?
Well,
That one has L, K, and
yeah. This is really plates. Are the numbers the same? 42, 46, and 50. Yeah, they're the same. He just figures you'd refer over here.
Okay.
And
And then the plate did fall in. I guess the cake or
The thickness.
whatever. Yeah.
right. See, the only reason you have the different things is because of more of the impurities being rolled out. So whether it's rolled in a plate or whether it's rolled in an angle, this angle used to be a plate,
Right.
or that whatever it is used to be, something that was a bar, and then they rolled it flat.
Right.
So yes, that's where you get your numbers from.
Okay. Okay. I have a couple more questions. But I know
All right. Let me just make sure I'm ready to go, and then I can get out of the way when the next guy comes in. You took this down here for 40 feet. I don't think there's any way it would really work, because these bolts would hold 80 till they went up into the ultimate range, and then they'd break before this bolt down here even knew what was going on. So you'll find in the specifications you will pay a penalty if your bolted connection is too long, and they're taking that into account. Here's a plate. It's got 900 kips on it. At ultimate load, there will be 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, gee, that's convenient. 9 bolts. And therefore, 100 kips will fall off of each bolt. It's just like water running down a trough. This hole is big enough to let 100 gallons a minute out. You're putting 900 gallons a minute into the trough. When I ask you what is the flow right here, you would say 900 gallons a minute. If I ask you for the flow of water at this point in the trough, you'd say, well, that trough has a hole in it, and it let out 100 gallons a minute, so how much gallons a minute is left? 800 gallons a minute, and that's how much load is left. So there's 800 kips going to flow across this pair of bolts. Take out 200 from 900, it's going to leave you 600 kips of load at this row of bolts, and on the last row of bolts you'll have 300 kips trying to break across that line. Now, if you study a break line that goes across here, you'll have to reduce the load trying to break across those two bolts. And you say, well, why aren't they all 80s? Because until these bolts fail a little bit, allowing this plate to stretch. See, if this bolt doesn't do a little bit of this, then the plate behind it hasn't moved. So until it has a little bend in it, no load gets on through because the plate isn't allowed to move, and so you don't get any load. But at 80 kips, they're deformed pretty enough that the plate right here can stretch, and then about 20 kips comes out these bolts, and then you get no bolts, no plate, no force. Increase it to about 400 kips. The 80 runs on up to about 90 each. About 70 each comes out here. About 30 makes it down into this pair of bolts, and about 10 make it down into that pair of bolts. And these bolts here say, huh? Nothing down there. Nothing made it because the plate hasn't stretched down in that region enough for those bolts to pick up some load. Here's 580 kips, 100. Now you see these bolts have gone plastic. They have deformed like that. You know, they had 100 in them when they only deformed maybe this much. And then they held 100 when they deformed that much. And they held 100 when they deformed that much. So they got 100, 100, 60, 20, 10. Here's 760 kips applied. 100, 100, 100. These have all failed fully plastically, but they're still holding the load. 50 got down to here, 30 got down to here, and finally, which is where we design it, all the bolts are equally loaded. Now you can take that to extremes. If you notes, gross area for a plate, just the 2 dimensions of the plate, net, 2 dimensions minus the number of holes that you cross as you go through a tear line, times the diameter of the hole, which is the diameter of the bolt, plus a 16th plus a 16th, times the thickness of the plate. Sometimes that's not the whole story. For plates, this is good, but for angles that are bolted only on one leg and have an outstanding unconnected element, you will have to reduce it by a reduction factor. Those are listed for different cases. Diameter of the hole, diameter of the bolt plus a 16th for fit, damage, effective area. In this region right here, you do get a stress. Down in here, load over area gross. Down in this region, you get load over area net. And it's increased by you, or the load is decreased by you. Take your choice which way you work it. There's your net area. Now, how bolts really work, here's a plate. Put 200 kips on the plate. I'll tell you now that I tested these bolts. Around 80 kips, they get a little deformed, but they'll go on up into the yield range and keep picking up load. At 100 kips, they're just pretty much trash. So out of 200 kips, the first load hits the first two bolts and 80 kips on each bolt drops out. Then that leaves, 88 is 160, that leaves 40 kips in this region right here. Okay, let's get started. As I mentioned before, a lot of these pages are from previous years, nice pictures, stuff like that that I just throw in because I think they help make the point. We were working on fasteners. We were working on Was ist los mit dir? I don't know. Don't do that again. We were working on the fact that sometimes when you bolt something like an angle, the load had to come down out of the top leg and go down in the bottom leg, and you lost a part of the angle, thereby making it less efficient. This is for staggered fasteners and how you handle the loads in a plate or an angle under those conditions. We mentioned that the length of the line, should the tear line decide it is too hard to fail it across here, it's just easier to go ahead and skip over to the next hole, even though it's longer. We mentioned that there were tensile stresses and shearing stresses. You would normally think, let's just take this total length across here, then find this squared plus that squared, take a square root, find that length. How much ever longer the hypotenuse is other than the leg, you just add that amount, you'd be okay. Physically, that's true. Structurally, it's not true. What we've really found is if you go from this hole, don't go straight across, but move over to this hole, the previous length of this line is increased by s squared over 4g. This was our spacing. And this was our gauge, like the gauge of a railroad that runs down the tracks in the direction of the load. So this original length leg of the triangle is not that much longer, but it's that much longer, and that works out really close for the structural strength. And it includes the fact that it is longer, but also that different kinds of stresses are acting on the plane, other than just nice old tensile stresses. There's several reasons why you would do staggered fasteners. Number one, if you put them side by side, you do destroy 2 holes worth of strength, and you don't pick up any extra length, so you may want a little extra strength. Sometimes the member itself is slanted with respect to what you're connecting it to, so when the load comes down, it sees no holes, 1 hole, maybe 1 hole in that hole, and so on. There's your S, there's your G.